Hello, everybody, and welcome to the DeFi Security Summit monthly webinar. We have actually one important announcement. As some of you seen, we have selected the venue for DeFi Security Summit this year. The event will be held before Devcon in Bangkok in November, and we're actually going to start selling tickets soon. And the second announcement is today we actually have two of the leading uh, uh, DeFi protocols, Aave and Balancer, and we have actually the top developers there. They will present the new development coming for DeFi this year. And we have Tomer Ganov, who is a lead security researcher at Satora, who's going to moderate the discussion. So Tomer, take it from there.
Thank you, Muli. Okay, hi everyone. I'm Tomer. I will be moderating this webinar. We have Emilio from Aave that will show us a new approach to how to determine the interest rate of Go, technical issues, and solutions to those issues. So take it away, Emilio.
Amazing. Thank you, Tomer, and thank you, everyone. Thank you, Muli and Sertora, for the invite. Always nice to be participating in DeFi Security Summit related activities. For those who don't know me, my name is Emilio. I am currently VP of Engineering at Avara, Aave Labs. And I have been involved since the beginning of the development of the Aave protocol. I have been participating and leading the development of all the three versions of the Aave protocol. There is always a lot of work around it. Recently, the Aave DAO has introduced also a decentralized stablecoin named GHO, and the GHO is integrated with the Aave protocol, so it kind of acts like CDP stablecoins, where users can access the Aave market and borrow natively GHO against the basket of collaterals that the Aave protocol supports. But in reality, Go is way more flexible than that. It's not just a CDP-based stablecoin, but it also has the capability to natively allocate allowances of the stablecoin to eventually other protocol or other products developed within the Aave ecosystem that can basically extend the capabilities of the stablecoin to be minted in a variety of different ways. You can think, for example, of it would be possible, for example, in the future to have we call them facilitators. So there can be natively allocated facilitators decided by the Aave DAO that can allow minting Go in different ways. So for example, you can imagine that in the future, the Aave DAO might explore a way of generating Go that is similar, for example, to what Ethena does. So like delta neutral strategies, or that Go can be extended to support real world assets, so that it can be collateralized by real world assets, and so on and so forth. There are a variety of ways that the Go design can extend the usability of Go. One of the major challenges that we have been facing in the current in the usage of Go with the current ways that Go is supported, so within the Aave protocol, is to maintain a strong and reliable peg. There are maintaining as a stablecoin peg is I would say multi-faced aspect, because it kind of involves a lot of different complexities that need to be handled at the same time. One of these are certainly appropriately determine how the interest rates for borrowing Go are calculated depending on the state of the peg. I will share my screen now so that I can use like the help of some slides that I prepared. Let's do it. Okay, I guess you guys can see the screen. Can you confirm in the chat if the screen is visible? Okay, perfect. So amazing. So let's go straight into it. Okay, now I shared full screen. Can you still see it? Okay, perfect. Amazing. Okay, let's go forward. So with these slides, I will present a new approach that we are designing for the Go stable coins for determining the right interest rates to maintain a healthy peg and still manage to propel the growth.
Invisible.
Now okay, just give me 1 second. I think I need to share not this I will share the whole screen. Just give me 1 second, because I share the window, but usually I think it doesn't work when I go full screen. Okay, now you should be able to see my screen, and now you should be able to see.
Yeah, now it's okay. Now it's okay.
Oh,
great.
Yeah, sorry. I just shared the window, but then it doesn't work when you go full screen. Ignore, please, like this Telegram icon that for some reason appeared here and doesn't want to go away. I need to run some commands to reset the window manager. But anyway, so let's go back like a notch. So what's a stable coin? As I mentioned before, it's a kind of a digital assets that tracks the value of an underlying real world assets. So we are mostly used to think of stable coins as cryptocurrencies that are pegged to the dollar because they are the most widely used within the crypto space. But in reality, we can define a stable coin as anything that tracks the price of an underlying asset, which basically brings a whole lot of challenges in terms of generation, redemption, and stability mechanism. So we can separate. I usually separate the stablecoins in three main categories. At least those are the categories that we have been seeing explored in the last couple of years. So we can mention certainly over-collateralized stablecoins. So this is the approach that currently Go uses, but again, it's not strictly restricted to that particular design. It can be expanded with other designs to explore different ways of generation. So in over-collateralized stable coins, usually the stable coins are generated against a volatile collateral at a fixed price. So in the crypto space, like decentralized stable coins use other crypto as collateral, so we can Bitcoin, Ethereum, Aave token, whatever other token that is suitable to be collateral. But it can also be, of course, against real-world assets. So, for example, Maker has the real-world part, where part of the assets backing DAI, specifically real-world dollars, are allocated, for example, in short-term treasuries to generate yield. Centrally controlled are, I think, the most widely used at the moment. Like we can mention Tether, we can mention USDC. There is a central entity that controls the generation and a redemption mechanism against the actual real-world asset. So simply put, users go to the central entity. They deposit, in the case of USD-based stablecoins, they deposit real dollars, and they get a representation of the real dollars that they deposit on chain. they can also go to the centrally controlled entity, and this entity can also exercise redemption by getting back the minted on-chain minted stablecoin and returning the dollars to the users that is actually redeeming. And then we have algorithmic, which I'm famously well known because of the spectacular crash of last year of Luna, where there is no collateral, essentially, neither real world or volatile, but the mechanisms of redemption, generation, and stability are all three algorithmically controlled to try and match supply and demand. So I will focus on describing like the features that I want to show. I will focus on over-collateralized stablecoins, and specifically on their meaning through they reach stability. So I usually separate the mechanisms that allow a stablecoin to maintain the peg in soft peg mechanisms and hard peg mechanisms. So soft peg mechanisms are, for example, one of those could be like generation and redemption at a fixed price, which is what happens on the Aave protocol when Go are generated and redeemed. So when users generate Go, essentially the oracle price of Go is set at $1. So the generation happens always at $1. Whatever the price on the secondary market is. And the same is true for liquidation and repayment. So when a user repays one Go, it will always be valued $1, despite the price that the Go stablecoin has on the secondary market. Maker, for example, or Liquidity work exactly the same. Variable borrow rates. In this list, we can have DAI, Go, and CRV USD. So, like the protocols try to adjust the borrow rates that borrowers are paying to try and stabilize the stablecoin in the market. So the idea behind it is basically when there is a lot of demand and a lot of incentives to mint the stablecoin and to sell the stablecoin in the market, what happens is that usually borrow rates go up to compensate for the additional pressure of the peg and eventually rebalance the arbitrage opportunity so that borrowers are not that incentivized in generating the stablecoin anymore. There is a difference between DAI, Go, and CRVUSD, for example, because DAI and Go actually use a governance-controlled rates where the governance decides whether or not like the interest rates that borrowers are currently paying are correct, where CRVUSD used an on-chain controller that automatically adjusts the borrow rate very quickly. It kind of resembles more the way the behavior of other stablecoins on Aave rather than the behavior of interest rates set by governance, like in the case of Go. So you can imagine the rates that are set for Go are usually less volatile because like governance timings are usually longer, while in the case of CRVUSD is closer to an actually fully variable rate where rates can actually vary per block. So you have lower reaction time in the case of governance controller rates, but more predictability compared to a fully variable interest rate model. Lately, it's interesting to mention, there are some new interesting approaches. For example, Liquidity V2 will actually have user set interest rates. So users will be allowed to set their own interest rates, and their interest rate will actually affect directly their redemption risk. The redemption mechanism is in a hard peg mechanism that I will describe afterwards. But the interesting part is that there will be no separate entity that actually set the user borrow rates, but the users will be able to set their own borrow rates to better assess their own risk reward, or to delegate the capability to set their own interest rate to a third-party entity. So that's more or less covers current state of the market for borrow rates. And also there are redemption and generation fees. These are peculiar to LUSD, because like the liquidity mechanism is quite different compared to that of DAI and Go, where there is the current version at least, there are no interest rates, but there are generation fee or origination fee better when a borrower originates his position, and there are also redemption fees in case like redemption are activated. So what are these redemptions? We go to the RPEG mechanism part. The redemption are essentially the forced redeemability of users' positions against the stablecoin whenever the pressure of the peg increases. So as soon as there is an increased pressure on the peg for the stablecoin, the system will automatically start redeeming the less collateralized positions for the stablecoin in an attempt to reduce the supply and bring the peg to a more stable level. So let's go forward and let's talk about stablecoin borrow rates more in detail. So as I mentioned before, DAI, for example, has governance-controlled borrow rates, where CRV USD, here we go a little bit in detail of how they work. So for example, DAI, which is a pure CDP platform, CDP means collateralized debt position, like they have a very flexible system where different vaults with different risk profiles also have these different interest rates. So whenever the maker governance usually updates the rates, like you can see a screenshot of a proposal of the maker governance to change some of the risk configuration and borrow rates, they have the capability to adjust the risk and the interest rates that the borrower are paying per kind of vault. So every collateral will get its own personalized risk and its own personalized interest rates. While in the case of CRVUSD, we have an automated mechanism. The formula that is described here essentially calculates what the interest rate at a certain block should be. They use certain parameters of the system to determine the value of the borrow rate. For example, I can highlight here the peg keeper debt, the total debt, which is the total debt of the system, and the fraction of peg keeper that is targeted when in the attempt to stabilize the peg. So the peg keepers are a system that the CRV USD implemented to extend the capability of adjusting the peg. So the peg keepers specifically act when the stablecoin goes above peg, so it's worth more than $1, by injecting liquidity in the peg keeper module, and by evaluating how much liquidity there is in the peg keeper module, essentially the CRV borrow rate module determines what the borrow rate should be. So both of them have some pros and some cons. I kind of mentioned the pros before of the governance controlled versus algorithmically controlled. The pros is that, like, usually governance controlled give more predictability to the users. So because there are certain time interval needed for governance to enact its own decisions, this means that interest rates cannot change more quickly, and also in advance to what the interest rates will change to. But like it brings a lot of governance overload that you will need to actually model continuously the stable coin you will need to have participation, people voting the proposal to actually be enacted. And it's also very hard to estimate properly. The variable, on the other hand, like they act in a completely autonomous way. So there is no entity setting the rates, but they offer no predictability because like the peg and therefore the state of the system, therefore the interest rates can change per block. So ideally, what we are trying to model with Go is a stable borrow rate module that works algorithmically, but also offers some kind of degrees of predictability. So no interest rates set per block, so you cannot end up in a situation where you are paying at this block 3%, and the next block you are paying 25, for example, but rather have a mechanism that is algorithmically controlled, but change the rate of change of the interest rate. So if their interest rates need to go up, they will start going up per block, but with a certain speed, not directly to the target value. And the same when they go down. So when they go down, interest rate will start going down progressively and not going directly down to the value that is optimal, that is determined. This, I think, will offer the best trade-off between reaction times. So it's not as fast as a true variable interest rate model, but it's not as, but it's also more predictable than a truly variable interest model. So we explored a variety of possibilities here to be able to implement this variable borrow rate model and algorithmically controlled. The first model that we evaluated was using a PID controller. So what's PID controller is it's very commonly used in industrial application to control aspects of a certain system. So for example, temperature or the speed of your car using the cruise control. This equation here that looks particularly complicated. It's actually not. It's basically composed by three different terms. The first term that is the proportional, the second term that is the integral, and the third term that is the derivative. Each term controls different aspects of the variability of the system. So we have a proportional term that acts proportionally to the current error that the system is experiencing. So you can think, for example, from the current error as the delta from the peg that the system is experiencing. Then there is the integral part that basically acts on the historical of the error. So if historically the asset, for example, has been underpegged, there is a component of the system that gets balanced by the integral component. And then there is a derivative component that basically determines a contribution to the final control value that is determined by the derivative of the error, which means basically estimates how quickly the error is changing in the basically within a short time frame from the current time. So again, what do we want? Automated but predictable rates. Acceptable degree of latency, so not as long as the governance, but quick enough to be able to react to changing market condition. And we want this because we want a certain degree of predictability, which will basically offer an alternative to more traditional stablecoins that can be borrowed on Aave with pure variable interest rates. So the first iteration using PID didn't quite behave the way that we were expecting to, because this model is too simple to actually model such a complex system like a stablecoin peg. This is because we can, as you can see in the equation, we can only consider the basically different aspects of the error from the peg, but we cannot evaluate why the actual behavior of the peg has been like this. Like there are a lot of different variables that contribute to the behavior of the peg. So for example, stablecoin could go up in price because there is short-term surge of demand because, I don't know, a new protocol has launched a, I don't know, farming campaign using your stablecoin, and suddenly your stablecoin goes in a demand frenzy, but it's not necessarily a long-term market behavior that is driving the pegging, but it's a kind of a short-term event. And it's hard to, for example, model something like this with such a simple approach. So we kind of evaluated, I can suggest also there was a very interesting paper published by the Morpho team on the topic in a couple of days ago, which is very, very interesting. I'm suggesting like to give a read if you are interested on this particular topic, especially the part there is the modeling of like full-fledged theoretical optimal interest rate strategy, which for obvious reasons is hard to replicate on chain because it uses dynamic programming and it's very computational intensive. We found another way, which is a different approach of control theory, which is called fuzzy logic. So I'm getting close to the time, so I will try to be quick and trying to explain what fuzzy logic is. So it's a kind of a novel application on control theory on the blockchain because, as far as I know, no other systems are using it at the moment. It's interesting because it's very computationally inexpensive and it allows to model a system following human understandable reasoning. So it's pretty easy if you look at a system like a stablecoin. It's pretty easy to identify certain conditions for which your interest rates should react in a certain way. And they are pretty easy to translate in natural human language, but they are very complicated to model mathematically. The fuzzy logic kind of fits perfectly in this particular use case because it allows to represent a degree of truth between a range of 0 and 1. So it's an extension of the classical Boolean logic where something is either true or false, but like the essentially what this allows to model are degree of truth where temperatures, for example, as we feel them, are not super cold or not super warm. Like there might be a degree in the middle. Same behavior can be evaluated for the certain behavior of an aspect of a stable coin. So that's why we decide to use this particular system. So I will go very quickly here, but this would take probably a few hours of discussion. So the whole system is based on a set of rules where you define rules that are actually human readable. One example of rule is if the distance from the peg is very high and negative, then the rate of acceleration of the interest rate should be high, because if the peg of the stablecoin is going down very fast, then you would probably react in a way where the interest rates are rising very quickly. So this rule that is human readable can actually be translated in a computer readable rule with a set that defines level of truth for this particular rule. And then the rule can be applied to value actual crisp, they are called crisp value read from the system to determine the control value that is applied to react on the system. So in this case, the borrow rates. There are a variety of variables that we can use. The interesting part is that this can be expanded indefinitely with minimal to no gas addition, because like the rules are very, very cheap to evaluate. So we can use distance from the peg, historical from the peg, and rate of acceleration. So for these three already cover everything that is described in the PID controller. But then we can use, for example, additionally the balances of the GSM, which is the Go stability module that basically allows to increase the stability of Go using actual stable coins like USDC or Tether. The state of the secondary market, so you can evaluate with system and have participation in the calculation of the error. What's the state of the secondary market? For example, on a set of selected decentralized exchanges and so on and so forth. So what will happen is that like the system will define a set of on-chain rules. And again, the rules can be expanded indefinitely. And then we can read these values from oracles or directly from the system that provide the service, so for example, the GSM, and apply the rules to the value to determine the correction that needs to be done to the interest rates to improve the state of the peg. It can be expanded in a variety of ways. You can define the sets that define the degrees of truth in a variety of shapes. You can use the defalsification method in a variety of different approaches. So it's very flexible because it allows seamless expansion of the model and also seamless customization of the way that the rules are interpreted. So next steps are going to be building model in Python. This actually was done already. And because this presentation was already, it's been quite a bit that I have been presenting it. There will be a governance proposal and discussion to also showcase how the system would have behaved in the past. There will be comparison against the PID version of the controller that we implemented before, and then on-chain proposal and execution. So to finalize, stability is a very complex topic. There will be automated mechanisms that actually bring faster reaction times to allow for a better stability mechanisms. But even faster reaction times and better stability mechanisms cannot be developed separately from creating new use cases for the stablecoin and focus on growth, which is actually as important, if not more important than stability mechanisms. So that's pretty much it from me. I don't know if there are questions.
First of all, thank you very much, Emilio. So it seems like there are a few questions. Maybe we can do it in a minute. Someone, let me show it, want to discuss with you in length later. So of course, can talk with they can talk to you later. And also,
I see them. Yeah, I can take it.
Also, we have another question regarding to how do you estimate the likelihood of the code to the peg?
Yeah. Okay. So, for integrations, like the Aave GHO is, the integration of for integrations, the Aave GHO is the best place to look for collaborations or integrations. Go can be integrated is permissionless as just stablecoin, so can be integrated in a variety of ways. If there needs to be governance participation, I would say that the Aave governance.aave.com is the best place to start. And how do you estimate the likelihood? You don't really estimate the likelihood of the asset to the peg. You kind of evaluate what's the state of the system now, and then you react accordingly. So that's more how this kind of system work. Even the governance controlled ones work like that. It's really hard to predict if and when the stablecoin will depeg. It's basically the only way is to estimate what's the best reaction to bring the asset back to peg. I think it's pretty natural. All stablecoins have experienced and will experience the peg at some point, because there is no way to hardly tie the price of the asset in the secondary market to the stability mechanism. The only thing that you can do is basically react accordingly and as quickly as possible.
Yeah, we can't fight with the market, of course.
Yes, exactly.
Great. Thank you very much, Emilio. It was very interesting. And
Thank
now,
you guys, thank you for.
Yeah, thank you. And now we have Juan from Balancer to show us the new version of Balancer in comparison to the previous one. Juan, the floor is yours.
Thank you very much, Tomer. Thank you everyone for having me here. And yeah, so today this talk is going to be quite technical, and it's going to be basically a speed run of what we are building for Balancer v3. So yeah, I'm Juani. I've been working for Balancer for about 2 years now, and well, I'm leading the smart contracts team. So yep, let's get to it. Brace yourself and fasten your seatbelts because this is going to be a bit intense. So yeah, let's get to it. So in the agenda we have first a quick overview of what Balancer v3 is. To explain it properly, I have to take a step back and explain a bit how v2 works, how the architecture works in v2, and some of the pain points that we realized about it by building and operating it throughout the years. And then I can jump to v3 and actually explain what the differences are with respect to v2 and what the improvements are. So let's get to it. First, what is Balancer v3? It's a decentralized exchange. It's going to work with fungible liquidity positions, meaning that when you add liquidity to a pool, you will get an ERC20 in return that represents your position in that pool. It has a single vault, meaning that all the tokens for every pool in Balancer v3 will stay in a single contract that holds and manages all that liquidity. And it's also kind of optimized to some degree to hold yield-bearing tokens. Second of all, it's a DeFi platform, and this is also something that we are like building very strongly towards. And it's basically not only a DEX, but also a platform. We will like other builders to come on top of Balancer and build their custom pools and hooks that might have like interesting trading curves or strategies. And the idea is to facilitate that as much as possible. And finally, Balancer is also an ecosystem in the sense that besides smart contracts, we also have integrations with other protocols. We have an SDK team, we have a front end, all of that to interact more easily with the contracts. So yeah, it's not only about smart contracts. This talk is going to be mostly about smart contracts because it's my specialty. But yeah, Balancer is more than that. So let's take a step back and take a look at what v2 looks like. I'll first try to speak about like the architecture in v2. And v2 looks something like this. You basically have two main components, which are the vault, which holds all the tokens, and pools, which hold basically say how tokens shall be traded. So for example, you have weighted pools, stale pools, all of those have different trading curves, and basically have the pricing mechanism that establish how much tokens have to go out for a given amount in, for example. So, sorry. So how does this work? Basically, the vault both holds the tokens and also is like an API for external users. So users can call the vault and say, okay, I want to join a pool, basically adding liquidity. I want to swap token A for token B in a given pool, or I want to exit my position, basically removing liquidity from a pool. So users interact directly with the vault basically talk with the pools so that they know what to do. The pool tells the vault how to do the accounting. It's essentially what's the result of a given operation. The vault saves the accounting and settles the balances. So for example, if I'm trading token A for token B, the vault will tell you, okay, give me X amount of token A, I will give you back Y amount of token B. So first thing here that it's worth mentioning is that the vault is both a user-facing contract, but also the one that is immutable and holds the tokens. And that is a big deal. I will expand that a bit later. And the second thing is that token accounting is a bit separated from BPT accounting. BPT is basically the LP tokens that represent the liquidity positions in the pools. And this is because the pools hold the state of their supply on its own. So basically, the accounting for the tokens happens in the vault, and the accounting for BPT or the LP tokens happens at each pool. This means that the vault basically doesn't know about what a BPT is. So, for example, when someone wants to join a pool and add liquidity, basically the vault sends the command to the pool, and the pool is in charge of actually minting or burning tokens. In case of adding liquidity, it will mint BPT tokens. In case of an exit or removing liquidity, it will burn BPT tokens. And there are a number of problems that arise from having this split between token accounting and BPT accounting. So some pros and cons of this design. So we have token accounting split from pool logic, which is cool. That means that you can have a vault that hosts a token, but different pool types that you can build on top of the pool, on top of the vault, and then use them accordingly. The second thing is that you have efficient batch swaps. So for example, if you want to trade token A for token F and they are not in the same pool, you can basically do many hops between all the pools that you need. And you won't need to be transferring tokens back and forth, the user and the vault. And this is because essentially all the tokens are already in the vault. So basically, if you manage the accounting properly, you can just do one transfer for a token in and get your token out. There's also one thing that I haven't mentioned that much, but basically you can also have a relayer that is basically another layer to extend basically the user-facing API. And with that, you can basically do more complex operations. So for example, if you want to, add liquidity and then stake that liquidity in a gauge, you can do that. Or you can add more complex functionality that is outside of the vault. And you can also iterate on that and improve it over time. And the other good thing that is also a challenge is that the Vault API is flexible and kind of future-proof. This has to be this way because we wanted different pool types that we didn't know about when we first started building the Vault. So we needed the API to be flexible. But on the other hand, being flexible is a bit at odds with an immutable contract that you cannot upgrade at any time. So basically, that adds complexity, and if you do something that is not optimal, you have to live with it for as long as the platform is alive, which is basically forever. So yeah, there's a challenge between being flexible and having an immutable contract. The vault has to be immutable because it holds the tokens, and otherwise it wouldn't give the LPs any assurance at all, so there's no way around it. So the question is, how do we keep something that is flexible but yet immutable? The second thing is that, pool tokens separated from LP tokens or BPTs, keeping those accounting separated is a bit complicated because essentially if the vault doesn't know about BPT, there's no way to query what the result of an operation will be when you add or remove liquidity directly. We can do that in B2, but it's very cumbersome. And basically what we want from queries is, okay, if I add liquidity or remove liquidity, what will be the result of this operation? When I mean getting the result beforehand, I don't mean running a full simulation, but rather just doing a static call that says, okay, this is the result, and that's it. So that's a very desirable trait of a system, and it's something that in B2 is a bit challenging to get. Also, I said that the Vault API is very flexible, but it's also a bit complex. For adding and removing liquidity in particular, you always have to rely on encoding data in a bytes array and decoding that in the pool, and that is a bit cumbersome. And again, there's no way around it because it's already built in the vault. So yeah, we have to live with it. I said that the relayer is cool because it adds another layer of flexibility, but the problem is that it's even harder to query what's going to happen when we interact with the relayer. And the last thing is that besides the basic architecture, there are a lot of helper functions that are distributed. So for example, pause and recovery mode, those are two very interesting things. Pause is basically being able to shut down a pool so that it doesn't allow trading anymore. Recovery mode is what allows users to essentially exit in case there's a problem. You can enable recovery mode and you basically provide a separate path that basically always works and doesn't have any external calls. So even if a pool logic is broken, you can enable recovery mode and allow users to exit their liquidity positions. And that is fundamental to give users good assurances. Token scaling, basically pools need to do token scaling. So if you have, for example, USDC that doesn't have 18 decimals, you might need to do the token scaling at the pool level. And also, well, liquidity operations, I will dig on that a bit later. But essentially, there are many ways to add liquidity to a pool. And in V2, each pool has to basically implement all those ways. And what I mean with all of this is that there are many things that are common to pools, that common functionality that every pool will need. And in V2, every pool has to implement its own logic to provide that functionality. So we were thinking that maybe some of that can be moved to the vault so that there's a base layer that handles all of that, and pool developers can only focus on what's important, which is basically new invariants, new trading strategies, or things that are not basically piping and plumbing. So that's our question for V3. It's like, how do we keep the good while improving the rest? So now let's jump into V3 architecture. Before like hitting you with another diagram, let's go again with the list. Like, okay, let's keep the good and say, what can we add? So first of all, we want to split the user-facing API from the immutable vault. And this means that we'll need another layer that we can basically upgrade if we want, and can be more flexible and rich and like even do more complex operations, but that doesn't have to be in the vault. So it's going to be a sort of free layer, but it's going to be more integrated into the ecosystem in V3. The second thing is that, well, we should split settlement from accounting. And that means that, for example, when you do an operation of a swap, I don't want the vault to start sending me tokens back and forth, because that complicates the queries. So for example, if I can split the settlement time from the accounting time, that will help me in the queries, because I can just like run a function that only does the accounting without settlement. And with that, I can get a result of what's going to happen when I do the actual operation. When I mean settlement, I basically mean sending tokens back and forth. So for example, if I want to swap token A for token B, I can tell the vault, okay, what's the amount of token A that I need to send you, and what's the amount of token B that you need to send me. And if I can do that first, and only then when I know the result, do the actual settlement, then I can do the queries basically for free. The other thing is that keeping the token accounting and BPT accounting together, all in the vault, will also help us to do the queries for liquidity operations. So that means that if all the accounting is in the vault, I can know what will happen when I add and remove liquidity, which is also very cool. And finally, what I was just talking about solving the developer experience issues at the base layer. So basically, all the things that are common to every pool, we should move them to the vault as well, so that pool developers can focus only on what's important. So now let's try to look at what V3 looks like from a workflow standpoint. So the workflow is something like this. The user sends a request to something that is the user-facing API. It's not going to be the vault in this case. That contract is going to open a tab at the vault, in the sense that telling the vault that, okay, start registering all the things that I'm going to do. It could be a swap, it could be adding liquidity, removing liquidity, or a combination of those. That's fine, because the vault will register every operation. And at some point when I'm done, I have to settle. If the user-facing API is able to settle correctly, meaning basically paying the debts to the vault and taking the right amount of tokens out of the vault according to the operations that have been done, then we can finish, everything is correct. But if it's not settled, we just revert as if nothing has happened. So this design is, the idea is to provide much more flexibility. We can like add much more complex operations in the middle. And if something is not paid for at the end, we just revert. So I won't dig that much, but the V3 architecture looks something like this. What I want you to take out from this is that now we will still have the vault and the pool, but we also have the router, which is the user-facing interface. The router can be replaced. It doesn't matter, because it just operates with the vault. And it can do like with combining simpler vault primitives, it can do like more complex stuff. And everything should still be queryable. And the other difference is that, again, token accounting and BPT accounting will all live at the vault. So that's how we can query liquidity operations. Again, those are the two things that I want to take out from this call. We'll have this router, vault, and pool architecture. All the accounting will live in the vault, and the workflow is always like, okay, let's open a tab, start registering all that we do. No matter what the combination of operations is, it's going to be fine because the vault registers everything. And only after I'm done, I can settle. If everything is settled, I can finish. If not, everything reverts. One note about this is that all this opening the tab and registering all the operations, now we have transient storage for this, which is storage that only lives within a transaction. And that is a great fit for this design because we can essentially store everything in transient storage. That doesn't go away within the transaction, and that's exactly what we need for this design to happen. So a summary of the traits that I have described so far. We can settle at the end. That means that the whole design is queryable. Simpler vault in the sense that we don't need to maintain a very complex API because the router will do that. And basically the vault has to be safe in terms of like reverting unsettled transactions, keeping pool balances isolated, same as in DB2, meaning that if there's a bad pool that does math wrong, okay, that's fine, but it shouldn't drain the rest of the vault. And then maybe pull some of the responsibility of like the common layer of the pools back into the vault so that every vault has the same treatment. Again, the router and the external API is upgradable, which is great. That means that you can potentially come up with something that's better. For example, if you need a router that adds liquidity and then stakes, you can just build it and it will work. And finally, another not so minor issue is that this design also supports reentrancy. As you are always like keeping the track of like what's going on, you can basically do swap within swaps or like adding liquidity before a swap or like start doing weird combinations or more complex operations that include like even modifying the pool balances within an operation. So for example, if you want to swap, but for example, add liquidity to the pool before you swap, you can do it. Or if you want to remove liquidity after you swap or whatever, you can also do it. So what are the DX improvements? This is also very important. As I was saying before, basically we want to push all the things that in DB2 are done by the pools directly to the vault. So essentially token scaling is pushed to the vault. I will skip the second one, protocol fees. That's also something that was partly handled by pools in DB2. That's also already handled by the vault in DB3. Post window, that's also something that pools needed to do in DB2. Now the vault can do it, and it's the same for recovery mode, which means that whenever you build in DB3 a pool, you get all the protocol fees handled, but also you get the post window and the recovery mode essentially for free. And that means that as a pool developer, you don't need to care about like a mechanism to actually post the pool in case something goes wrong. You get that already for free. And you also get like a escape hatch in case something goes wrong again. You can enable recovery mode to allow users to exit their positions in a way that is meant to fail basically never. The second item is a bit more complicated, and this is related to like how you add or remove liquidity from a pool. So in many basic the AMMs, you basically have to add liquidity proportionally and remove liquidity proportionally. For 2 token pools, that's maybe not that bad because you can basically like, I know, if I only have one of the tokens of the pool, I can swap half of it and then add proportionally. But then if you have, for example, 4 token pools, it starts becoming more annoying. So that's what unbalanced add and removes basically solve. There might be, for example, a 4 token pool. You want to add liquidity to that pool, but you only have 1 token. Then you can do an unbalanced add liquidity with only that token. That is a bit of a complex problem because essentially it's more or less of a swap plus an adding liquidity all in the same operation. It has price impact, of course, but it can be solved. And it's something that we put some thought on, and we found a way that is a bit better with respect to V2. So this is a small chart that summarizes like ways of adding and removing liquidity. So for example, imagine that you want to add liquidity. Again, you have only one token, and you want to specify like, okay, I have, I don't know, 10 ETH. I want to add it to this pool, and I just want to add 10 ETH. I don't care if the pool has 4 tokens or whatever. So that's basically an unbalanced single token exact in add liquidity, because I want to like add an exact amount in, and I only have one token. Same for remove liquidity. I usually have like, I don't know, 10 BPT. I want to exit all the position or half the position, so I give it like, I don't know, 5 BPT to the system to burn, and I get my liquidity out, or I give all of it and I get all the liquidity out. So this is more or less the add and remove liquidity types that make sense. So in the case of unbalanced liquidity, both exact in and exact out for single token makes sense. Unbalanced multi-token and liquidity also makes sense. Maybe there's a 4-token pool, you have 3 tokens or 2 tokens, and you want to add both of them. You can also do that. And of course, proportional. For remove liquidity, it's more or less the same. The only one that doesn't make much sense is unbalanced multi-token liquidity. You usually, when you want to exit liquidity, you either want a proportional exit that doesn't pay any fees, or you want to just exit in a single token. And both you need exact in and exact out, and I will get to that very soon. But essentially, it allows you to control either the amount that you are adding, in case of the adding liquidity, the tokens that you're adding, or the amount of BPT that you get out, and vice versa for removing liquidity. This is important for batch swaps when you have composable pools, and I will get to that really soon. So the problem is that in V2 you could do all of this, but the problem is that the pools needed to basically know how to do this and have a method that solved, okay, if I want to add liquidity and balance single token given in or exact in, okay, I need to have a function that explicitly does that. Same for given out, so each type had its own implementation. This was okay, and it works in Balancer V2, but the problem is that if you are building on that, you might not want to do all of that, because basically you can, just by adding liquidity proportional, the pool will still work. It's just that it won't be like so user friendly. So we found out that some integrators that built on Balancer V2 really didn't care about all of this and only built with proportional joins and exits. So in Balancer V3, the idea is that the DX for building a pool should be much easier, and instead of providing like one explicit method for each of those add and remove liquidity types, we can just do with 2 functions. One that is called compute invariant and compute balance. The details of these are like a bit intricate, but essentially the point is that every pool with fungible liquidity should have a sort of invariant. If you expose the way to calculate it, and you also expose a sort of inverse invariant, which is compute balance, the vault resolves all of that for you. So essentially, by implementing these 2 functions, you get all of the add and remove liquidity types that are relevant for Balancer V3. Of course, on top of that, you need to implement a swap function that is optimized, because that's basically the key of a pool. And finally, another important thing of building pools on Balancer V3 is that we also have this pool lifecycle. And as I said before, you can do actions like before swapping or after swapping, or before adding liquidity, after adding liquidity, and same for removing liquidity. And the actions that you can do in those instances are basically unbounded, because you can, as I said before, if you're swapping, you can add liquidity to the pool before you're swapping, or you can add liquidity to another pool, or basically you can do whatever. You can also go to another protocol, do some arbitrage, or go to Aave and close a position and then come back. It's like, the idea is to make this as flexible as possible to provide opportunities for builders. And finally, a practical example of putting all of this together. Let's say that you have a pool, the first pool, pool A, with DAI, USDC, and USDT in some form of yield-bearing tokens. So basically, this is a sort of boosted pool where the assets are actually lent to Aave and earning yield. Then you have a second pool, pool B, which is the BPT of pool A paired against wrap stake ETH. And then you have a pool C of wrap stake ETH against BAL, for example, a weighted pool that is 80-20. The second pool is very interesting because it's essentially like a yield-bearing pool that has all the most used stablecoins. It could be also Go, for example. And that's earning yield at Aave, and it's paired against a yield-bearing version of ETH. So you have all of that in a single pool, which essentially gives LPs lots of sources of revenue, not just swap fees, but also yield fees coming from Aave and from Lido in this case. So if you want to swap, for example, DAI for BAL, the swap path will be something like this. You have to add liquidity first, essentially get DAI for pool A. That's adding liquidity and getting the BPT for pool A. The second step is swapping that BPT of pool A for wrap stake ETH. And the third step is swapping wrap stake ETH for BAL. And all of this, which is a fairly complex swap, which has adding liquidity in the middle, can all be queried and executed in one transaction, no matter whether it's like exact in, meaning that I specify the amount of DAI, or exact out if I specify the amount of BAL. So yeah, as you can see, the design is very flexible, and all of this is given as long as the pool developers implement those three functions. And you can then extend it with your imagination. You can pair, like do different sorts of composability or different trade paths. But the idea is that you can always query what the result will be, and you can always execute that in a single transaction with minimal transfers, because in this case, you should only transfer DAI at the beginning and get BAL at the end. So I think that was it. I hope you enjoyed it. It's a bit intense, but yeah, it's a speed run of what we are building for Balancer V3. Yeah, now open to questions.
First of all, thank you very much, Juani. It was very interesting, of course. And if there is a question from the audience, feel free to write in the chat, so we can ask. In the meanwhile, I have a question regarding you said before in the example, you had the yield-bearing tokens there, like you had the ADAI and you had also STETH and everything. And my question is, like the middle pool, the second pool that you had there, you said that you can get multiple sources of income, but a user doesn't have it doesn't get a compounded amount of yield, right? They get like a partially divided yield from each, and then it's proportional, like it's more diversified income, right?
Correct, exactly. Point. Correct. So when you LP the second pool, you essentially own a piece of wrap stake ETH and a piece of the pool that has tokens lent to Aave. So yeah, it's not that it's compounded, but it's diversified by just LPing one single pool.
Yes. So practically, when I have a BPT of the second pool, the one with wrap stake ETH, and the BPT from the first pool, I effectively have 20% or some percentage of ADAI, some percentage of wrapped ETH, wrap stake ETH, and all of that. And then if, for example, I don't know, for some reason the Lido wrap stake ETH has less yield, we still have the yield from Aave in some proportion.
Correct. That is correct.
Yeah. I see we have a question. Let me just show it on screen and then you can read it. So, yeah. So what was the main security consideration, if there is one, that you kept in mind while coding Balancer V3 smart contracts?
Okay, that's a tricky one. I would say that we try to strive for simplicity, and you have to take that with a grain of salt, because at this year we are not in 2017 or 18 anymore. It's not that you can like build Uni V2 and be successful, because that's already been done. So we try to make things as simple as possible, and particularly when it comes to invariants or things that are very critical, such as maintaining like pool balances separated, or like ensuring that everything is settled at the end. Those pieces of code should be like very easy to reason about. So that makes them easier to test, and basically that improves your chances of that being correct. If those mechanisms are complex to reason about and harder to test, then that makes it much harder for it to be successful. So yeah, we always try to, like I said, that we push a lot of complexity into the vault, but we really thought what is justified and what's not, in the sense that if it's a 10x improvement for the system as a whole, then we can push it in the vault. But if not, it's out of the way so that it's not part of the immutable contract that is very like the centerpiece of it all.
Yeah, so the complex stuff are out, the simple stuff are in the vault, and the rest is super simple.
Exactly. Yeah, exactly. So basically, like separating the API, for example, is one step in that direction, because like if you have simpler primitives in the vault, it's easier to reason about them. Then you can mix them up, but if every primitive does its job properly, then you won't mess up. I mean, you're just like combining things that work all together.
Can you give an example? I see there is another question. When is V3 coming out?
Soon. I mean, yeah, we've been building it for several months now. We are a bit delayed because we are still tweaking some things. But yeah, hopefully in the next few months.
Great, and I have another question regarding, you said that you tend to make everything as simple as you can. Is there something that is too complicated to have in that if it was simple you put in? Or too complicated for now at least?
Well, for example, I mean, batch swaps, I mean, that example that I just said of like trading token A for token F, and they are not in the same pool, and doing all that swap path that potentially has adding liquidity and removing liquidity in the middle, that's super complex. In Balance RB2, actually, that is part of the vault, and the vault has to need some help from the pools to decide whenever there's adding or removing liquidity. So that part is like super complex, and we basically took that out from the vault. So now basically if you want a batch swap, the router will do that for you by combining simpler operations at the vault. That's one example.
And if the router is wrong, then the vault will just revert everything, and then we don't care.
Exactly. Another example is wrapping and unwrapping native ETH. Again, in Balance RB2, the vault wrapped and unwrapped native ETH. That turned out to be a problem. So now the vault only handles ERC20 tokens, and the router is the one that has to wrap and unwrap in case there's native ETH involved in the operation.
Yeah, that makes sense. I wouldn't expect the vault to do such operations if you can just outsource them.
Mm-hmm.
Yeah. If there is any more questions, feel free to ask. But I think that's it. Thank you very much, Juani. It was very interesting.
Thanks to you.
Also thank you to Emilio from before. And I think that is everything. Thank you everyone from joining us. And have a good evening or good morning, depending on where you are.
Thank you very much. Pleasure.
Thank you. Thank you, everyone.